what I'll be doing first is to present the elementary data structures, KD trees, right? And then in a second step, I'll present you the refinements which allow one to get theoretical guarantees. So KD trees, in fact, so the idea is very simple. The idea is actually reminiscent from these binary search trees I mentioned, namely the red-black trees or the AVL trees, which essentially aim at splitting the data set into two equal subsets, right? Because if you do so, of course, you are going to end up with a balanced data structure. And so, so here, the punchline is the following. So we are going to assume for KD trees that we have an embedding. So we can, let's say, a Euclidean space, so points have coordinates. And so a KD tree is a binary tree, right? And so it has a root, and so the root points to two subtrees, the left one and the right one, right? And so the root actually will come with a so-called hyperplane, and so this hyperplane is going to split the entire space into two regions. And so here on this example, this is actually the hyperplane associated to the root, right? So I'm splitting my square into two regions, the left box and the right box. And so how is one choosing, and of course the left, this is going to be the point set associated to the left subtree, and this is going to be the point set associated to the right subtree. And as you can see, I'm storing a particular point in the root, right? So of course I didn't tell you so far how I'm picking this, how I am defining this plane. But in any case, what can be done is to, if you take this rule for granted, you have a way to pick a plane and to split actually the point set into two subsets of equal size. So then, of course, you do this recursively, right? And then you stop once you have at most n not n zero points in a leaf, right? Okay, so this is the idea of building a KD tree. So typically, so this is in fact the algorithm, right? The pseudocode. So what should I say here? So for KD trees, originally, the split rule selection has been very simple. So you pick you iteratively iterate over all coordinates. So to begin with, so you pick the as a coordinate. So let's assume that we are in dimension 2. Right? So you pick the x-axis as a coordinate, and now you project all points onto the x-axis, right? And now you compute the median, namely the value which is leaving as many points on the left-hand side and on the right-hand side. So if you have done that, in fact, so you know how to split your point set into two equal subsets. So right, using this plane, namely the plane which is running through the median, namely through the point whose x value is the median of all values projected along the x-axis, right? Is it clear? So you take a direction, maybe the x-axis, you project, you compute the median, the value which is separated into two subsets of equal size, and then you split here, full stop. So that's what the pseudocode is telling us. And in fact, so you stop if you have reached your stop condition. And the interesting thing here is that well, the only thing to know, to decide, is how to pick, well, how to pick the split rule for nodes down the tree. And so the first guess is typically to cyclically iterate over all coordinates. So if you're in dimension 3, you split at the root, you split along the x direction, and then at depth 1, you split using the y direction, and then the z direction, and then if you need to iterate along the x, y, z, and so on and so forth. So you cyclically iterate, visit all coordinates, right? Okay. So this is plainly the construction of a standard, I would say, KD tree. So now, of course, arises the question of searching a KD tree, right? And so this is quite interesting because there are a number of ways to do that. So now we are going to assume that we have a query point, we have a KD tree, and we want to figure out n and q, the nearest neighbor of q, using the KD tree. And so in fact, I'll be presenting 3 strategies to do so. So the first one is known as a defeatist search. You are going to understand why. So this is like, you know, in algorithms, so there is this notion of greedy strategy. In a greedy strategy, you make a decision and you stick to it, right? And so the defeatist search is a greedy search strategy using KD trees. So it's very simple, but it may fail, right? And so whence actually the other alternative. So the descending search is a method which is a bit more complicated, which is going to return the exact nearest neighbor in all cases, except that it is a bit more time consuming, right? And so finally we'll see this priority search strategy, which strikes a compromise between the defeatist search and the descending strategies, right? The priority search is trying to get the best of both worlds, namely returning the exact nearest neighbor using a decent complexity. Okay. So the defeatist search actually, so I put the pseudocode just in case you would like to take a look to it. But in fact, so it's quite easy to explain. So let's assume that we have our KD tree here, and let's assume that our query point is Q. So again, you have the root of the tree, and the root comes with a split rule. I split my data set along the x-axis, and here is the median, right? And so again, the median is sitting here, right? And so it turns out that Q has an x value which is smaller than the x value of the median. And so I'm saying, okay, so then let me visit the left subtree, right? And so let me try to find my nearest neighbor in the left subtree. So therefore, I recursively step into the left subtree, and then of course I have to do this recursively. So I enter this node, which now has been split using the y direction, right? And so here is the point which realizes the median value of all samples located in the left subtree, right? And so it turns out that I'm sitting now on the right subtree of this node, and so I'm going to recursively descend into this right subtree. So again, so this is a greedy strategy. You make a decision, you go to the right, to the left, and you stick to it. So what is the problem? Well, obviously the problem is that you can be wrong, because in this case, look, if I'm selecting the nearest neighbor of Q in this actually subtree, so let's say this is this guy, right? Okay, so this is the nearest neighbor which my algorithm is going to return. But if you you forget about the KD tree, and you start growing a ball at Q, your nearest neighbor is sitting here, right? So your nearest neighbor is not located in the tree which you visit, right? And so in fact, so the strategy is doomed to fail from the very beginning. So you make a decision, but right away it is a wrong one. And so of course, this is not very good. So the good point here is that you descend down the tree which has a logarithmic height, and so you know for sure that you are done in log n steps, but the caveat is that you may get a point which is not the correct one. Okay, and so now, of course, what we are going to do, we are going to take a look to two strategies which fix this problem, and later on, I'll be introducing this beautiful construction known as random projection trees, which actually provides probabilistic arguments saying that if you don't use splits perpendicular to coordinate axis, but splits which are made at random, namely using random directions, then with high probability you will get the right neighbor anyway. Right? So this will come later. But for now, let us try to fix this problem using the descending search. And so in the descending search, in fact, the idea is to visit one or two subtrees depending on the distance which has been computed so far, right? So, so typically you need to compute a bound tau, right? Which is actually a guess. Tau is a guess for the distance between Q and NQ, right? And so now the algorithm goes as follows. So you initialize tau with the distance to the sample contained in the root of the tree, right? And so at any step, so this gives you, you know that you have a ball. You have already found a ball. You have already found a neighbor which is sitting on a ball of radius tau, right? And so now here is what's happening. So when you are actually traversing down the tree, So you are going to visit one or two subtrees, and when do you decide to visit a tree? Where? Well, remember, a node has two neighbors, right? A node has two subtrees, a left subtree and a right subtree. His subtree corresponds to a domain which is a hypercube, right? It is a box. And so what you do, you compute the distance. Actually, you check whether the sphere centered at Q with radius tau intersects the domain of the left subtree, and likewise with the domain of the right subtree. And of course, if you intersect this domain, then it tells you that potentially you have a neighbor. If in that domain you have a neighbor sitting inside the ball of radius tau, so then this point is actually a better guess for your nearest neighbor. So here is the situation, right? So if you are sitting here, so obviously, so with respect to, as you can see, with respect to this horizontal split here, so the defective search would tell you, let's visit the subtree corresponding to this region, except that, again, your best nearest neighbor is sitting here, because in fact, as you can see, this distance is shorter than this one. But of course, now if you are checking the condition, does the ball centered at Q and of radius tau intersect the domain of the second subtree? So here the answer is yes, and you are going to step into this region. Right? And so this way, you know for sure that you are going to collect your nearest neighbor. So in other words, the take-home message here is that the value of tau ensures that the top cell actually will be visited, namely the cell containing the nearest neighbor. Okay, so it turns out that if you do that, you'll be happy all the time with the nearest neighbor, except that you may end up visiting a large number of cells. And so there is a final refinement here, which is known as the priority search. And in the priority search, actually, one is trying to minimize the number of nodes, or equivalently the number of regions which are visited. And this process actually uses a priority queue, right? And so let me show you the pseudocode here. So it's a bit complicated, but actually, let's take a look to the picture. Let me try to explain the idea. So what's going to happen? So again, we are going to maintain a distance bound tau for the distance between the query point Q and its nearest neighbor, right? And so whenever we are traveling down the tree, so if we are in this situation here, so obviously, like in the defective search, we are going to visit the subtree which contains the node. So this is for sure. But again, there is this problem which we already described 2 or 3 times. If your nearest neighbor is sitting on the other side of the fence, so then you should also visit this box. And so the idea here is, as opposed to the previous strategy, the idea is the following. By default, do not visit this tree. Instead, put actually this node into a priority queue with a priority which is in fact the distance between Q and the cell, right? So you are saying, okay, so since Q is sitting in a region, let me visit the cell containing actually the cell whose region contains Q. But in case my nearest neighbor would be sitting on the other side of the boundary, let me keep the possibility to visit this subtree too. But we keep the possibility without doing it in any case. And so the process again uses the priority queue. So we remember this node or this subtree. We put it in a priority queue with a priority inversely proportional to the distance, right? And now the iteration actually, is over the priority queue. So as long as the priority queue is not empty, so you pick a node. And so what you do is in fact, so you check that, so this node has a region R, right? And so what you do is you check that the distance between your query point and this new cell is still relevant, meaning that this distance should be, If this distance is more than the bound tau you have collected so far, so then you know that you have found it's actually useless to visit this region, right? Because this algorithm, as you see, is putting nodes into a priority queue, and then is living its life. And then what's happening is that a node is getting popped from the priority queue, may get popped a while after it has been pushed into the priority queue, right? But between the push and the pop, so the bound tau may have evolved. And so if you have found your nearest neighbor, if you have a short value of tau, and if actually the cell we are talking about is too far with respect to tau, it means that upon popping this region R, so the region is irrelevant, right? And so this is the way actually things are working. So this way, you are going to report the nearest neighbor in any case, but in fact, you minimize the number of nodes you are traveling into. Okay. So if I wanted to recap here on this nearest neighbor search using KD trees, so using this priority search, so you always return the nearest neighbor. So it's also good because, of course, this is plainly a KD tree. And so once it's using linear storage, except that the caveat is that when people have tried to evaluate this data structure and this search algorithm in practical settings, in fact, it turns out that in fact it is quite costly because you have to maintain the priority queue, and if you are unlucky, you will be visiting a large number of nodes, possibly linear in the size of the tree, and so this is not actually a very good option. Okay, and so of course there are a number of people have tried to ponder on this problem, saying, okay, so KD tree, this is a beautiful data structure, so linear size, so these search algorithms actually they are not fully satisfactory because the simplest one do not return the nearest neighbor, and if you want the nearest neighbor, you sometimes have to pay a lot, and so what can we do? And so a number of ideas have been proposed. And so these ideas actually are essentially threefold. Stopping the recursion once a fraction of nodes has been visited. But of course, if you do so, you take a risk. So this is not very good. So something more interesting. What about using overlapping cells, right? Because of course, if what we have used so far is a KD tree which defines a partition of the space, right? And of course, troubles are arising when you are sitting in a cell and when your nearest neighbor is on the other side of the boundary. And so in fact, so what about using overlapping cells? So in fact, so by duplicating the points, by storing them into two cells, so that could help. So don't worry, I'm going to discuss this in details. So this is one option, which indeed actually turns out to be a great one. And finally, another option consists of getting rid of the strategy which is only using coordinate axes to run the splits, right? And so option number one is not so interesting, but option number two is yielding so-called spill trees and virtual spill trees, which I'm going to explain in detail. And option number three is actually yielding so-called random partition trees or randomized partition trees, which are a simple generalization of KD trees where the splits are made along random directions as opposed to coordinate axes. Okay, so if you want to learn about KD trees, so these are the two classical sources, right? So you have this encyclopedia by Hanan Samet. So it's, I think this is possibly the book which the most comprehensive book on actually data structures to run searches. It's about 1,000 pages long, right? And you also have a more recent book here. Actually, Samet's book came into several versions, so it's been sitting around for almost 20 years. And recently, so the book has been enlarged to take into account recent developments. If you care more for theoretical algorithmic aspects, so you should possibly take a look to the second book edited by Piotr Indyk and colleagues.